The ERMAC Centre is proud to present the SFU Canada Research Chairs Seminar Series. This bi-weekly series hosts 6 presentations per semester. For the fall 2008 and spring 2009 semesters, the presenters belong to the Faculty of Science and the current Faculty of Applied Science. Today's speaker is Dr. Bojan Mohar. Dr. Mohar will present his talk entitled, How to Draw with a Small Number of Crossings.
The subject of graph theory probably emigrated to Canada with Bill Tutt when he came to Toronto in 1963 and came into its own a couple of years later with the founding of the Department of Combinatorics and Optimization at the University of Waterloo. This far-sighted move initiated a complicated chain of events which very happily led to the outcome a relatively few decades later of Bojan Mohar making a decision to join Simon Fraser University as a Tier 1 Canada Research Chair in the subject of graph theory. This has been a very wonderful development for our department, which has been one of the major poles of discrete mathematics in Canada, in North America, and increasingly in the world, because of not only Bojan's activity, but because of the activity of many people who have preceded him and who are still here working to develop this subject by bringing in many talented young and middle-aged and old researchers who are seeing just an incredible amount of activity. And Bojan has shown a great deal of extremely valuable leadership in doing this. So this is very exciting for us over the past little while, seeing this come to fruition. Bojan Mohar got his PhD in 1986 at the University of Ljubljana in Slovenia with a thesis titled Graphi v kombinatorični topologiji. And I don't think anybody's going to read that today, so you can ask Bojan for a copy if you want. I was thinking of going on to MathSciNet to get an easy count for the publications, but I ran out of time. But I can tell you simply I got tired of turning the pages before I got to the end of the list in Bojan's CV. There's an enormous productivity, but going along with that enormous productivity, there is wonderful quality, and this has been recognized in a variety of ways, not only by the Tier 1 CRC. Bojan is a very active player, not just in the production of pure mathematics in graph theory, and I was interested to look at his CV and in addition to the remarkable publications that have been appearing in the past short period of time, also to see that he's elected to be the vice chair of the SIAM activity group in discrete mathematics, and also recently nominated and elected to be a regular member of the International Academy of Mathematical Chemistry. So this diversity of activity is all part of the research leadership. So I hope you'll join me in welcoming him as he comes to give us a paper on a subject that maybe some of us thought we knew how to do, how to draw a graph with a small number of crossings. Bojan.
Thank you, Tom. It's for a working mathematician, it's extremely difficult task to make a talk which would be public talk and understandable to larger audience, as I would like to do today. And so the choice of my topic is not a coincidence, so I'm choosing something that I hope everybody here would be able at least partially understand and appreciate. And I will start with some motivation where this crossing number minimization, which I'm speaking towards in the second part of my talk, comes from. The title is How to Draw a Graph with Small Number of Crossings, and I want to start with a couple of examples showing some graphs drawn, which I found on the internet, and the problems which about crossing edges which come along in those drawings. So relation to graph drawing and crossing number minimizations goes from mathematics to many other areas of science. Some of them are put here, like web science. This is a very new science, is looking at the network of the internet, for instance, and other networks related to it. VLSI Design, that's a design of very large-scale integrated circuits. That's an important subject in designing the highly efficient and very large integrated circuits for computer processors and so on. Data mining. This is a very data mining and data visualization. This is a very active research area lately, because just with the growth of computer power and with the growth of internet connectivity, it is possible today to research very large data. And if you want to do some research, you have to do some statistical things or some visualization things. Sociology, I just observed when I was waiting outside before that there is a very active group at SFU looking at sociological networks. I'll show you a couple of pictures later: biology, biotechnology, and so on. So let's go to some of the pictures I have here. The one you saw before, it's a map of the internet, and I could say it's maybe early internet here. So this picture shows as points. Points would be maybe web pages or computers connected to the internet, and then the little lines joining them. You don't see many points because there are millions of them, but the little lines joining them would correspond their connectivity. Maybe one web page is linked to another one, and this shows the connectivity. Why would I say this is an early internet? Because today you would have one node which is connected to almost everywhere, or you have a couple like Google or Yahoo and so on. So those evidently were not present at the time when this drawing was made. Here is another picture of the internet map, dated back to 2001. So that was still, you can see the national clusters in here. So that's a kind of thing you would like to extract from such a drawing. So it's what's the structure of this connectivity. So you see the clusters, they probably correspond to the language barrier. So the biggest one is the English one. So it's not geographical, but it's just the connectivity here. But there is also a big Spanish cluster in this picture. Here is another that's more artistic visualization of a part of the internet graph. So it's a very artistic, but what I'd like to point out with this picture is that in order to represent this, you get lots of these links crossing each other. So the picture gets messy. So and this is the subject I'd like to discuss here. The next example is something from medicine or biology, biotechnology research. So researchers identified certain genes, and in order to see which genes would be related to the breast cancer, they had some kind of influence how they are related to each other, and they came up with such a graph. So this graph represents different genes, and connections mean something. So I'm not going to explain that, but you see that it's a lot of crossings in this picture. Our goal later will be to see what can we say about drawing such a layout and having the number of crossings of edges minimized. That's the basic idea. Here are some more graphs from genetics. They come The one on the right-hand side is something which you can actually work with, and it's a part of the big graph on the left side. So that's, again, it's a kind of genes and how they are related. And all these problems, another biological network, so this is not genetics anymore, it's something else. I'm not interested really to mention what about it is, but you see you get more or less structured pictures. This one is very messy, yeah? And another biological system, so the nodes, maybe I'll take a minute to describe the notion of the graph at this point. In a graph, we have nodes or vertices, and different, like represented by these little ovals or circles, and then the different nodes are connected by edges. So that in the models like this one, the edges have some meaning. Maybe this corresponds to some animals, and the two animals are related if their genuses are somehow close to each other. Protein folding, that's a big problem in biology, so that's another picture. In medicine, people have studied different diseases and relations between them. So some disease is related to another one, maybe if they are more likely to occur simultaneously. And so it's so this is a graph of some kind of classification of diseases, and you see this mathematical task of making this graph nice and readily visible. Here's another graph with lots of edges. It's just related to some research done on obesity, how the different factors influence each other for the obesity. It's a quite complicated graph, I would say. In sociology, people study sociological problems. So here is one. Well, this one is more like doing relations between research journals. So this graph here, the vertices, these little points, there are very many in these big clusters, represent different scientific journals across the publications. And the edges between them, for instance, here are represent, or closeness represents how often two journals cite each other. Of course, it is likely that journals in the same area will cite each other, but the journals in physics will cite medicine or vice versa. That's less likely. But this sociological research showed a kind of interesting grouping. So the mathematics is close to physics and computer science. Medicine is close to chemistry, plant biology, and so on. So again, we come to a problem of drawing this graph nicely, and so that we can get some information from it. Here is another. It's a graph which I found on the internet. It's about research topic networks. So it's a small area of research where there are different research topics. Actually, it's about graph drawing. So it's different problems in graph drawing, how they are related to each other. And it occurs that you can see these clusters identified with different colors. It occurs that some types of drawing some kinds of types of drawing are more closer to each other. Well, but that's just coming from this picture. And here is another application. I know that criminology department is also active here in Ermax. So this was a graph related to investigation of the 9/11, the Homeland Security problem. So it's the nodes, the vertices of this graph will represent some flights and some pilots. And whatever the meaning of the edges would be, that's probably secure information, so I'm not going to try to explain that too much. But you see, the idea here was probably to look at this graph and get some automated version what you can say. So if you find some very strange thing here, you can maybe just use this to help the Homeland Security in an automated way. Last application I want to mention is VLSI Design. So this is a design of electrical networks, which you can print on the either integrated circuit board or inside a processor. And here you have an example of this is just made a drawing of some circuit, and which maybe results in such a piece of hardware there. And you see, in this circuit, there are many electronic elements connected to each other, and there are many crossings. And if you put the circuit on the plane, it's like drawing it on the piece of paper, yeah? And the crossings must be somehow taken care of by taking the wires. So this is the graph of this circuit has many crossings because you can see how many wires they have used to eliminate these crossings. So that's a kind of a general problem related in VLSI design, is just to minimize the number of crossings in order to get a simple layout for the electronic circuits that you're producing. Here is another one that's a bigger electronic circuit. So today, these electronic circuits have not only millions, but even billions of elements. So it's an area of very huge, large graphs. So after this introduction, I'm coming to the notion, to the mathematical notion I'd like to discuss in this talk. It's about the crossing number. And we'll go from these big graphs, from these pictures with examples which are small graphs, because this is something we can understand. So let me start with a definition. So suppose I have a graph like this one, given by vertices and interconnecting edges, and I would like to make a drawing of the graph. And in the drawing, what I want is that the number of edges crossing each other, number of pairs of edges crossing each other would be minimal. You see the picture on the right, I took this edge, and instead of making two crossings here, I redraw this edge here, and it was only one crossing that occurred. So the right-hand side picture is better in this respect. So instead of 5 crossings here, 1, 2, 3, 4, 5, I only have 1, 2, 3 crossings. And the crossing number of this graph would be the minimum number of crossings you can get. So we can get 3. It's a nice, challenging question. Can we do with 2? So can we draw this same graph with only 2 crossings? And I hope you won't get lost in the later part of my talk, but you can try yourself. Can you do this with only 2 crossings? And that's where mathematics comes from. Yeah, that's where mathematics is needed to prove that maybe you cannot, or of course, if you find a better picture, then it's even better. But let's just remember from this slide, the crossing number of a graph is the best way, is the minimum number of crossings occurred in any drawing. This concept is relatively old in graph theory. One of the first papers, I think it's not the first one, but one of the first papers about this subject was written by Paul Turan. This is a Hungarian mathematician. He, during the World War II, he was forced to work in the labor camp in Hungary. And it was a brick factory. And this brick factory had certain productions of bricks, so kilns, Let's say there were 3 kilns. And then from each kiln, they transported bricks along a little railroads to the storage, let's say storage yards. And as you see, from kiln A, you want to have a connectivity to each of these storage yards because you don't know which ones will be empty at the time you need. And what it occurred is when they were pushing these trolleys from site A to site Y, they had to cross some of the rails, like the one connecting B and W. And this was very, very hard because the bricks would fall down and trolleys would have problems and they had to slow down and so on. And so the question which Paul Turan made was, well, maybe design this network of rails connecting the kilns and the storages so that the number of crossings is minimized. And that's exactly the crossing number problem. Actually, I must admit I don't understand why he was trying to minimize this. I would suppose that people who were forced to do in the labor camp would tend not to be cooperative with the Germans. So he would maybe like to have a design with most number of crossings. And actually, there was a German mathematician, Heiko Harbert, who worked for many years on this other type of problem. So what is the worst drawing of a graph that you can have the most number of crossings? So that's a kind of paradox. So the Germans would do the converse. And Turan's, so this is known today as Turan's brick factory problem, is actually how to draw this type of a graph with the minimum number of crossings. And this type of a graph, which appears in this particular problem, it's a so-called complete bipartite graph. I'll mention this later, so let me refer to it. It has the property that you have certain number of vertices on the left, certain number of vertices on the right, and then every vertex on the left has an edge going to the right. So this is so-called complete bipartite graph. And there are 2 parameters. It's the number of vertices on the left, so this is 3 in this case, and the number of vertices on the right. And it's denoted by KMN. So I'll use this symbol later on. So it's when I say graph KMN, it means like this, K34. This is K34 in this case. So it has 3 vertices on the left, 4 on the right, and all edges in between. That's a complete bipartite graph. So this brickyard problem is still open today. So nobody knows what is the best solution to it. That's amazing. So it's, you see, it's, as I started, it's difficult to say what a research mathematician would do. What is a problem which is interesting? Here is a problem that a child can understand. So how to draw this thing in the best way. And it's still largely open. So there are many results about it, but it's still a largely open problem. So for this general complete bipartite graph, KMN, there is actually a conjectured solution. So Turan found the following possibility to draw this graph KMN. Actually, even Zarankiewicz, that was. You have m vertices on the left and n vertices on the right. And what you do, you put your left vertices on a vertical line, like these pink vertices here. And you put half of them on the upper part and half of them here. So let's say everything is divisible by 2, so this is easy. This can be done. And then the other vertices, the right-hand side vertices, you put on this horizontal line. Again, half of them on the left, half of them on the right. And then you see the edges will go, every green vertex is adjacent to every pink vertex, either here or here, and so on. Yeah? So this is just the drawing of this complete bipartite graph on 8 + 8 vertices that we see here. So this drawing is conjectured to be optimal. Nobody is able to find any better drawing. And after so many years, we believe this is actually best. And this is true for every MNN. It's conjectured that it is true. And if you count the number of crossings, you come to this handy formula. So it's m over 2 times m minus 1 over 2. These are just integer parts, so it's just forget about it if you're not familiar with notation. So it's roughly m squared over 4 times n squared over 4. That's the number of crossings in such a picture. And actually today, nobody can prove this is optimal. So the problem here is lower bounds to show that why can we not get something which is better than this? Paul Erdős, it's another Hungarian mathematician, one probably most known graph theorist, besides Bill Tutt, that was mentioned before, introduced the following problem. It's a purely discrete geometry problem. You are given some points in the plane, let's say n points in the plane, like this purple points here. Oops, sorry. Like this purple points here. And then the question is, if you look at all 4 tuples of vertices, you take all possible 4 tuples of vertices, how many of them are in convex position? The convex position means like the ones, these 4 vertices. And if they are in convex position, if you draw all connecting edges, you get a crossing. If they are not in the convex position, you don't get a crossing. And so this was this very discrete problem, just points, no graphs, but you can formulate it as a crossing number problem. Because these are your points, you just draw all edges, and then you see that the number of crossings that you have is precisely the same as the number of convex 4 tuples. Because every crossing, let's look at this green crossing here, involves 4 points. And since it is a crossing, these 4 points are in convex position. So that's it's exactly the same thing, except that you are not allowed to draw edges. You must draw edges by straight lines. And so this is just a version of the crossing number problem called rectilinear crossing number. It's another version of the problem, but I won't go into the time and explain differences between the two. So Erdős' problem was really just about the crossing number of. So that was about the minimum number of such crossings. You can also ask about the maximum number of crossings, but that's easy. That's an easy problem, because what you can do, you just put your points on a circle if you want, and then any 4 tuple is convex. So take any 4 points, they're in convex position. So to maximize this is easy, but to minimize it's very hard. Now, I've shown you before the complete bipartite graph, the one with the brickyard problem. Yeah? So the conjectured layout, which everybody today believes it's optimal drawing, but nobody can prove it. A similar thing holds for another very simple graph. Just take a graph which has n vertices, and then any 2 vertices are connected by an edge. That's a complete graph, and the notation is Kn. So here I refer to this notation. You will see it later. So just remember, Kn means a graph where it has n vertices, like n is 100 vertices, or 48, like here in this picture. And every pair of edges, every pair of vertices is connected by an edge. And here is a layout which is conjectured to be best possible for drawings of Kn. And it goes as follows. We take half of the vertices of this Kn and put them on a circle, and another half on a bigger circle. And then you connect the edges on the inner circle just by straight lines across, like here. So I've now drawn all the edges. You get many crossings, as you see. And then for the edges on the outer circle, you draw all the edges outside. It's a similar thing. So if you think of this on a cylinder, this would be the top of the cylinder, and this would be at the bottom of the cylinder. You can visualize maybe this in this way. So for this vertex and this vertex, you draw the edge outside. But it will be a same number of crossings as in this part. And for edges in between, you choose this vertex. You just draw the edge in the shorter direction. So it's either here or whichever is shorter way. You don't go with an edge all the way around, but you choose the shorter direction. So that's here is the second part of the drawing. So I've drawn all the edges in between, and I won't bother you with the outside edges. That will be too messy picture. And this is conjectured to be the best drawing of this graph. This would be K48, and nobody can prove it. So I will mention a couple of results stating what is known. So here, this is a conjecture. It was made by Richard Guy. Richard Guy is another Canadian mathematician. He didn't work only in graph theory. So he was famous because he had a problem session in what is it, monthly or this was one of the problems. So he conjectured that the crossing number of the complete graph satisfies this formula. And this formula comes from the drawing, the cylindrical drawing I shown you before. So that's it takes some time to compute, but it's exactly that formula. And nobody was able to prove this. So for small graphs today, it is known. So like if you have 2 vertices, 3 vertices, that's easy. But all up to 12 vertices. And I would like to mention that the result for K12 and K11 is very recent. It hasn't been even published yet. So it's a recent paper submitted for publication, and it's been using lots of computation and some computer optimization, some new methods, semi-definite programming, and so on. So it's a kind of area which with today's computers you can progress a little bit. And but it's you would wonder why mathematicians would be interested in drawing graph on 12 vertices. This is just one graph, so it is important actually. So if you get any bound, any improvement on this problem for n equals 12, you get an improvement on this conjecture. So a corollary of, this is what is known today, that for the crossing number of Kn, it is smaller than this conjectured value of Richard Guy, that was in the previous slide, so, and which comes from the cylindrical drawing. And it is known, the lower bound, it is known it is at least 86%, roughly 86% of that. So this is all mathematicians could prove today. So 86 of that. So it's still far away to go. So, but this bound has been largely improved in the last decade. So it was much worse 5 years ago. Now I want to show you one proof in my talk. So it's I only have 10 minutes left, but I'm going with one proof. Now, it's a general audience, I guess, but that's what mathematicians do. So we prove a theorem. So it's for us, a theorem is a proof is everything. It's not only art of doing mathematics, but it's also a technology. So it's like making a device work. So you get a proof, you design something, and this design is made so that it proves some result. So is it important or not? It's a different side. But here is crossing, so-called crossing lemma. This is an important result which was obtained about 25 years ago by two independent groups of researchers. Tom Layton was doing VLSI Design. He's a computer scientist originally, so he was doing VLSI Design, and he proved this lemma independently from Aitai and others. It says the following: if you have a graph which has lots of edges, there is certain bound, so let's say at least 4 times n edges. This 4.5 could be decreased to 4 times n, I guess. Then the crossing number is really large. And really large means this is like the number of edges cubed divided by n squared. And this is the right size of the magnitude. For complete graph, the number of edges is like roughly n squared over 2, because you have all possible edges between vertices. So this would be roughly n to the 6 divided by n to the squared. So it comes to something like constant times n to the 4, which is the right order of magnitude. If you remember this Richard Guy bound, that was n to the 4 times a constant. So this is, but this gives a bound on every graph. So how do you prove this? This proof some people consider as a book proof. Paul Erdős made a definition what the book is. So for him, as a working mathematician, the book would be written by God, and each page would contain the most beautiful proof, the most elegant proof of some theorem. So there is one which is, well, of course, we have different criteria, but there is, for some things, there is a proof which we all agree is the best one. And this is like a book proof, almost. It's like a book proof of the result. So what I'm trying to show is that if the graph has many edges, then it has many crossings. And the first step is very easy. This is a kind of a graduate, on a graduate level of or even undergraduates meet this bound. It's so-called Euler's formula, which says that if you have a graph which can be drawn without crossings, then this graph has at most roughly 3n edges. So that's Euler's formula. At most 3n edges, forget about the 6. It's just but if you have a graph on n vertices and no crossings, then it has only about 3n edges, not too many. So if you have more than these edges, take your optimal drawing, and then just there is at least one edge which is crossing. Remove that edge. You still have many edges left, so there is still a crossing. You remove that edge, and so on. And what it turns out, you see that the number of crossings is at least e minus 3n. So that's an easy formula, but this is far from what we try to prove. This is linear in E, not cubic. Yeah? We want E cubed. Now, for this, what we do is we do some amplification of the previous inequality, and it's done by a probabilistic argument. Probabilistic argument is something that statisticians would do. So what you do is you have your graph. It has n vertices and e edges, and then you take a random subgraph. What do I mean by a random subgraph? I choose a number between 0 and 1. This will be a probability, certain probability. Let's think about 1/2, okay? And then, so 1/2 is nice. 1/2 means you flip a coin, yeah? And then for every vertex of your graph, you flip a coin with this probability. And if it comes tail, you take that vertex. If it comes head, you remove that vertex. And this way, you get some vertices, and then you take also all the edges between those vertices, which are in the graph G. So that's this random graph. And we have the Euler's formula bound that the crossing number of this graph is at least the number of edges of this graph minus 3 times the number of vertices. So that's on the previous slide, but now the miracle here is that you can take this is a random graph, so it's a random thing. And randomly, when you do randomly, you think of the number of crossings of this subgraph. It's a random variable, the number of vertices, number of edges, and you can take expectations. So you can take expectation of this for this inequality, and you get that the expectation is just the average. The average crossing number that you get with your random choice is at least the average number of edges minus 3 times the average number of vertices. Now, this works. It's all basic mathematics. And the miracle is that you can easily compute these averages. So let me do one of them for you. So let's do the number of vertices. So you flip a coin independently for each vertex. So how many vertices you expect? Half of them, yeah? But the probability is p. You get p times n, yeah? So that's the expected value of the number of vertices of this random graph is p times n. And what is the expected number of crossings? So I have chosen some vertices, and some crossings have been left. Now, to get the crossing, I must have chosen all 4 vertices that make that crossing, that make the 2 edges crossing. And so the probability that I have a particular crossing left in my G prime is same as p to the 4, because that's the probability that I have selected all these 4 vertices. Well, the total number of crossings is equal. We don't know what the crossing number is, but we're saying suppose we have an optimal drawing. The total number of crossings is CR of G. So the expected number is p to the 4 times CR of G. That's just the average argument. And so you just plug in these expected values. It turns out into this p to the 4 times crossing number is at least this value on the right-hand side. And just to continue, so we came to this. Now what you do, you just choose a good probability. So maybe 1/2 was not good, you choose something better. And what it turns out, you do some basic calculus. It turns out that this probability is actually the best you can do. And if you plug the probability of this form, then you get the crossing number is at least, you remember, e to the cubed over n squared divided by a constant. So in the theorem, the constant was, I'm not sure you remember, it was 33.75. But that was another paper, so that takes more time to prove. But just to get this bound, this is something that undergraduate mathematician can understand, and some people say this is the book proof. Well, one of the book proofs for. Now, towards the end, I'd like to ask a more general question. So if I have a graph, maybe one of these graphs that people in sociology produce, how hard is it to say what is the minimum number of crossings that I need? And even that, having that, maybe how to draw that, but that's a kind of additional information. But even what is the minimum number of crossings, that is very hard. So I mean, it's more or less intuitively it's obvious, because we can't solve the problems for even very, very simple graphs like the complete graph with no structure, no real structure. It must be hard. And the underlying notion, it's NP hard, NP complete. So that's what people working in complexity theory understand very well. So what is more surprising is it is hard for anything you can imagine. So this is a result that I proved last year with Sergio Cabello, that actually, even if your graph is very simple, it looks like something which you can draw without crossings, like in this picture, the blue subgraph, and then you add one edge, one extra edge. Well, this particular case, it's easy. So what is the best drawing? But if you just have an input, your blue graph, and then 2 vertices, and you add one the red edge, what is the crossing number of this graph? It looks easy. It looks you can develop some theory, and you can, but still it is NP hard. Now that's an amazing. It's an amazing fact about crossing numbers. Anything you try to do, it's hard. And this, I'm going towards the end of my talk. I just want to say that mathematicians work on this. So there are many exciting new results in this area. We're still far from the very basic one and basic understanding, but that's what we hope the time will bring. Yeah. So just to conclude, here is a possibility of getting rid of crossings. It's an Escher type drawing. So I'd like to thank you for your attention. Thank
you, Bojan. We have time for questions. We are recording this, so please use mic.
In the proof of the crossing number inequality that you gave,
Yeah.
How can you interpret the value of p that you chose in the end?
Well, if you just there is no real interpretation, but I mean it's you see it's a basic calculus to see what will give you the best result. Yeah, so you just take what gives you the maximum, or well the maximum on the right hand side. So, but you can see one thing here. Oops, I'm sorry. Where was that? You can see one thing here, that this probability is 4n over e. So if the number of edges would be less than 4n, this would be bigger than 1. So there was this assumption at the beginning of the crossing lemma that the number of edges is large enough. Yeah. And so that's, for instance, that's the only interpretation I could give. But it's basically people have been trying to do other things. So this is a common proof method in crossing number theory. So to get lower bounds, you take subgraphs and then you're saying, oh yeah, each of these has this many crossings. So altogether I have this many. So you get involved counting arguments. But this probabilistic argument is really bringing some new, really new powerful amplification to this. It's all over mathematics that proofs of this type give a better result than classical enumeration things. Yeah.
So you told us that the smallest open case of the conjecture for the complete graph was 13 vertices.
Yes.
What's the smallest open case for the bipartite graph, the brick factory problem, please?
It's around 7 and 8. So so things like K8 has been solved, and then if one parameter is 6 or less, that is known. That has been known for decades, so maybe 40 years. And a case when one side has 7 vertices and the other one is maybe big, there was a considerable progress just made by semi-definite programming. So this was made by a group at University of Waterloo. They get considerable improvement of bounds, and that also led to improved bounds for the general case. And then with 8 vertices on both, at least 8 on both sides, well, 8 is understood and maybe 8 9, but anything bigger than that is probably unknown. So yeah, yes.
So it's difficult to compute the crossing number, but it's easy to decide if the crossing number is 0. Okay, if the graph is planar.
That you can do in linear time by the well-known.
When I say easy, it's already a complicated proof, but we know how to do it. So how far can we go in that, or did people go in that? Answer the question, the crossing number is blah, blah.
Yes. So let me just make a short argument for crossing number at most 1. You can do this very easily, because if you just guess which 2 edges would cross, you identify that crossing into a new vertex. And then you just check if this graph has no crossing, so you test planarity. Yeah. And there are polynomially many choices which two edges would cross. So you just check all pairs, and that gives rise to a let's say, efficient algorithm. And this has been generalized for every k. If you want to test if the crossing number is at most k, fixed constant, let's say k 100, there is a polynomial time algorithm. But so this was proved by Kenichi Kawarabayashi, who was, maybe I should just mention, he's actually still visiting us, but he's just flying back to Japan after 2 years now today. So Kenichi proved that this can be decided in linear time, and the proof relies on graph minors theory. So it's a complicated proof, and the algorithms are also complicated and not practical. Theoretically they are good, but not to be used in practice. So for fixed number of crossings, you can do it, yeah, at least theoretically, and nothing else. So.
One question. Another question? If not, let us thank our speaker again.
The focus of the SFU Canada Research Chairs Seminar Series is to provide an opportunity to the wider SFU community to learn more about the current research interests of the SFU Canada Research Chair holders. Our next presentation will be on March 12, 2009. Dr. Randall M. Peterman will present his talk entitled Research for Improving the Understanding, Conservation, and Management of Pacific Salmon Populations.